Okay. Now, we are at the second phase. We were trying to get to why or whether a reaction occurs or not. Whether a reaction is going to happen. What's one of the factors? I can illustrate it right here. Where's this pen going when I drop it? To the ceiling. Yeah. It's going to go down. It's going to go to the lowest energy state. That's not the same thing for entropy. As a matter of fact, I've got a neat little illustration of that on a video. Okay, we're going to talk about entropy today.
I can't wait.
And the abbreviation for entropy is an S. Okay. All right. Let me show you my little thing here. Yeah, turn it off.
That's what I did. Very good. Oh, the marbles one.
Yeah, remember this?
Yes.
Exactly. Now watch.
I tried to find that on YouTube, but it's not.
Just watch.
Yeah, just watch.
Okay. There's no sound in this one. Just watch. Now those are a bunch of mixed up marbles. They are awful mixed up. Now this person's going to shake them, and something very strange is going to happen here.
Are they normal marbles?
Just watch. We did this in Chem 1, one of the first weeks of school, the first week of school.
Nobody's saying it.
Watch. Don't say it out loud if you know what's going on here. Notice those blue marbles and those brown marbles are separating.
Segregating.
It's
segregation.
yes, that's right. They're racist marbles.
That's what I'm saying.
Yep. Separate but equal. What happened there?
North versus
Don't
south.
tell it. Don't
Say it. Think. What happened?
One marble's heavier than the other one.
Jesse, you got to know this.
Nope. This is where the first thing that drove me crazy with Shania. All right.
What did she say?
Well, I'll tell you in a minute. All right, back to the entropy here. So look at that. Didn't look right for a reason. If you shake up a bunch of blue and brown marbles, all things being equal, they're going to get more and more random, more and more disordered. How did they do that in the video?
I want to hear Dave's theory.
Yeah.
Dave, what's your
They're
theory?
just straight magic.
It was straight magic.
Yeah.
Shania. I'm already calling you Shania. Whatever your name is, Dizzy. Dizzy over there thinks it's going to be because one's heavier than the other one. But it is funny, and I used this as a point last year about how we all teachers are idiots. You know, I hear every meeting. Every meeting, you hear people, teachers who think, "Oh, kids know technology so much better than we do." It's like that's not true. You guys didn't even pick up on it. Like the same thing last year. Nick knows. What did they do, Nick?
The video's in reverse.
They reversed the video. It's the simplest trick in the world. All right?
What is he asking?
Yeah. They reversed because I could tell he knew. I can just see it. Like,
Yeah, Dave.
Wait, you can do that?
oh!
No,
Yes,
but
you
I'm
can do
saying,
that.
like,
Yes.
you can just switch it.
Well, you can't really see that. Like, if you've never seen that video before.
Right. I understand that, but it's such a trick that that's the first thing you would think of. If like the first thing of people who are looking for it, you guys are looking for magic, magnets, heavy density, whatever. It was a lot easier than that. All I had to do was reverse the video, and the reason I had to reverse it is because we know that doesn't happen. Everything seeks its highest entropy state, its most disordered state. Okay, and that's what entropy is—a disorder in a system.
That's like when last year I went and asked my dad. I told him what happened, and his first thing was that the video played back.
Exactly. And this is back last year when I first showed this to you, I made that point. And I was trying to make that point with Shania today. Except that no. Well, that's not true. She has to argue over every little thing. But it is true. I think you guys are much better at using technology, but you really don't understand it any more than your parents or people who grew up with it. And the reason for that is we actually had to know how to install programs and fix things that went wrong with our computers. You guys just throw it out in a year and you buy a new one. That's all you do. Seriously. And I know it's easier, but it doesn't mean you are better at technology. You're not. And sometimes the simplest thing like that, you miss. You miss the forest for the trees. Anyway, back to chemistry, because I can't spend, like I did last period, 20 minutes yelling about technology. All right, absolute entropy is the measure of the disorder of a system. We all know, as from that video, it doesn't look right when things become more ordered. By themselves, they're going to become less ordered. They're going to become more disordered. All right, which means entropy is going to do what? Increase or decrease? Increase, yeah. Because entropy is how much disorder you have. So the second law of thermodynamics simply says this, and this is the second key to the puzzle of whether a reaction is spontaneous or not. It says spontaneous reactions are favored by an increase in disorder, by an increase in entropy. So just like it naturally see that pen drop to the floor, no one's going to say it's going to the ceiling. If I naturally shake up a box of marbles, they're going to become more disordered. And everything's like that in your life. I used Allie as my example for the next one. I said, Allie's hair didn't look like that when she woke up this morning. I use Allie's hair because you know what it looks like. All right?
No.
Exactly. Allie's hair has to be straightened in order for it to look that way, and it takes, probably a half an hour for her to do that. Things naturally become, when you wake up in the morning, you don't look like you look when you walk in here. Well, maybe Bulkley does, but everybody else looks like that. Most of you girls spend time making yourselves look better because you will look more disordered. Your hair is disheveled. You just don't look very good. Your rooms illustrate this. Your rooms become messy all by themselves.
How do you know what my room looks like?
I've been there.
Wow.
But it takes energy to put them back into order, okay? So things naturally, and you guys also illustrate the other one about seeing your lowest energy state like the pen. When you go home, you lay down in front of the TV, you don't do any homework.
Damn right.
That's pretty much lowest energy state,
Pretty much.
messiest, that's pretty much Allie, Bulkley, for every one of you. But again, you'll get an argument from Shania on every one of these points, which is what drives me crazy last period. All right, spontaneous reactions are favored by an increase in disorder, okay? That's the second law. Now, I don't, honestly, I write this in here because it's in here, and I honestly don't know why this is called a law. But the third law of thermodynamics simply sets the zero of the entropy scale. Okay, I'm not going to lie to you. I don't understand why this is an actual law. But I do understand what its implications are to our calculations. The zero of the entropy scale is set at an unattainable goal, an absolute zero, this infinitely ordered crystal that has no movement at all. Okay? Why is that important for our calculations? I can tell you that. I can't tell you exactly why that's called the third law of thermodynamics. Maybe I should look that up. I'm not smart enough to know that. By making zero on the scale, absolute zero, everything will have some entropy. You're never going to get a compound or an element that has no entropy in it. And that's the reason for that is, remember at the molecular level, we've done this before in Chem 1, things are moving. Even in a solid, even in a really, really cold solid, you have some Brownian movement, some movement of the molecules vibrating about a fixed position. Maybe not with a lot of energy, but you have it. Okay? So everything, even a solid, has some energy associated with it. There's never going to be a negative value for delta, for S, not delta, for S. Absolute entropy for any compound, anything you can think of, has to be a positive value. Because the alternative, the zero at the scale, is this infinitely ordered crystal that doesn't exist. You can't have absolute zero. You can't get there. I know. Well, the point is, it is actually nice to have only positive values. It makes our calculations, as you'll see, have tomorrow. You're going to be doing this. Our calculations are going to actually. There's an implication. I don't want to go any further than that. You'll see it tomorrow. All right. So that doesn't mean there can't be a change in entropy that's positive or negative. In other words, some of the questions in tonight's homework, which you only have. Oh, that's right. The red one up there is where we left off. I didn't give them the homework from the air stuff we did in the second half. Some of those questions are just going to be theory kind of questions. Like if a building falls down, a building full of bricks falls down, what happened to the entropy? Did it increase or decrease?
Increase.
It increased, right. Now, if I build a building from a pile of bricks,
It decreased.
yeah, entropy decrease. So I can have a change in entropy that is positive or negative. I just can't have an absolute entropy for any compound or element that is negative or zero. Things being goofy. All right. Okay.
Yep.
Now, so this change in entropy for a reaction is what I want to concentrate on, because that's what's going to be our second factor that's going to tell us whether a reaction is spontaneous or not. There's your equation. The change in entropy, delta S of a reaction, is going to equal. Notice the similarity between this reaction and the delta H of reaction. Isn't it exactly the same? Products minus reactants, right?
No.
Put a big box around that, just like you put a big box around the delta H one. The only difference being delta H instead of delta S there. So if I find the entropy of the products and subtract the weight, for the same logic of Hess's law applies, I can basically get the entropy change for the reaction. And if I get that entropy change to be positive, what is that going to tell me? If my answer to that question, which I'm going to do here in a minute, is positive, what's that going to tell me? Is that favoring spontaneity or not? If delta S is positive,
Yeah,
it's going to favor. If delta H is negative, what does that tell you? That's what it means, is favoring spontaneity, right? So those are your two factors. There's a third we're going to get tomorrow. But let's just do one example with this right now. Copy that question down. And we really want to do this one together, all right? Because I'm going to show you some of the mistakes you're going to make. Matter of fact, I've got 5 things written down to remind you about that you're going to make as a mistake in these problems.
We make 4 mistakes.
Yeah, what happens if we only make 4?
If you only make 4, you'll get an A. 5 mistakes that people make all the time. I want you to do this. Matter of fact, I'm even going to stop the camera because it's going to take you about 5 minutes to do this one, okay? And then I'm going to go over it and show you, and I'll bet you money you make at least 2 or 3 of those mistakes. Go ahead, try that guy. Plug them into the equation. Delta S of the reaction equals delta S of the products minus the delta S of the reaction. Try that.
Well, there's kind of a G bar that you won't get into.
Hurry up, come on, everybody try it, because I want to see what mistakes you're going to make. If you make the same ones, or if you even come up with some other ones. But these are the ones I've seen over the years, that's why I wrote them down. You should start out by writing delta S of the reaction equals, and give me the equation. I need that equation for any problems you do on the test. And you know what the equation is, delta S of the product minus delta S of the reaction. So do that. Where are you going to find those values, by the way? Appendix K. Yeah, in case, I just realized I haven't mentioned this yet, guys. But you've only been using the first column. Guess what the second column says at the top? Delta S, yeah, entropy. Actually, it says S. But try this guy. See if you get him right.
Should I still go make copies of this page?
Actually, I made them today. She actually did have a good idea about that. And unfortunately, the copy machine cut off the bottom of it, so I'm going to make you ones for tomorrow. I gave them theirs out, but they're going to have to get the ones.
Okay, whatever.
I don't want to carry this book around.
No, that's not true. You can't do the
Not true.
homework
You have
with
to
that.
carry around every day.
Yep.
It's very
Sleep with it under your pillow.
And make out with it.
Okay, that's getting a little
Yeah, that's a little.
R-rated there.
All right, come on, get to work.
Yeah, come on. Stuff to do.
we'll probably be able to tell by your answers how many different answers we get. What kind of mistakes you made, but we'll see. Who's done already? One? Just one person? Two?
These take time, Alan.
I know. That's why I'm with you. Do your wrong, Pete. Make your mistakes. That's what I want to see. Just looking up those values, plugging them into the equation. See what kind of answers we got. Lydia, what you get? Come on.
130.7.
Jesse?
732.
I love it. What else? Lizzie?
220.
Yes! So far, no two are the same. What else? Anybody else going yet? What do you get?
447.
My God, that's four. Four, not one of them the same. Come on.
I don't know. I got like 811.
811. Nice. Nick?
I got 447.
Ooh, we got two 400s.
That's right.
I'm still going.
I lied.
What?
I hit
plus.
How come we all have different?
We're going to get to all those mistakes. What'd you get?
818.
Yeah, the two 800s, though. Wow, what? We don't know which one's right now.
With both. What'd you get? 818.
That's true. Yeah, that's pretty bad. You got the same as both.
Poor bastard. You're wrong.
All right, let's do this thing.
This is dumb.
Now, look at. I wrote down the 5 mistakes. I'm going to tell them to you right now before I start it, and then I'm going to see which ones of those mistakes you made. Okay, so look at. Here are the 5 mistakes you can make. First one. Did you look up this guy, that guy, that guy? In other words, do the reactants minus the products. You just switch them around. Because that's what we did in the delta H at first, remember? That's an easy mistake to make. So the first number you should have looked up when you're doing this was not N2H4. He's a reactant. You should have looked up N2, right? So what is N2's value? 191.5, correct? If you don't have 191.5, and by the way, the units are not kilojoules by this time. What are they? They're what? Joules per mole Kelvin. Okay? Who doesn't have 191.5? Dayton, what'd you have for your first thing written down there?
Like 324 something.
Okay, why does he have 324? I have no idea, because that's not even one of the choices. I have no idea. But that could be one of the other 4 mistakes. Let's talk about this. Okay, here's another mistake. Looking in the wrong column. Up till now, you've used the first column everywhere.
Yeah.
Looking in the wrong column. Very easy to make that mistake. Number 3, looking up the wrong state. When I start writing these numbers down, some of you will have looked at water gas or water solid, all right, or one of these other guys in a different state. That's number 4, or no, number 3. Number 4 is forgetting about the coefficients. Somebody forgot that last period.
Can't forget about the coefficients.
And the last one is doing the math correctly. When you go to distribute this, you better have brackets around that guy because it won't come out right if you just plug them directly into your calculator. So those are your 5 mistakes. I'll go over them again at the end, but let's see how many of you made. We already know we probably had some mistakes made for this first one. I don't know, but let's see.
Where did you get 191?
Where did I get 191.5?
Where it says N2H4.
Where it says N? No, see, date. I just said that.
Oh, it's
You're reading left to right.
You're supposed to read that.
No, you're supposed to do it correctly. What's the equation say? Delta S of the what?
130.
Products. Is that a product? No, that's the product. So you look up N2. That's where you got it from.
138.
It's not that. Oh.
What's the
191.5. So what'd you do? Why originally you said it's not there. What were you looking at?
I was looking at kilojoules per mole.
So that means you were in the other column. Exactly why I said the second mistake was in the wrong column. These are all the mistakes you'll make. I know. How about it? Plus, do you have for your other guy 4? Oh, I only have 4 there.
I got 130.
Yep.
Because you're supposed to subtract, not add.
4 times what?
69.
69.91, you get that?
Yeah, I love 60.
Joules per mole Kelvin. All right. Now, this minus, better put brackets around this guy. Better have brackets around him because the two guys you're looking up here, all right, none of them are going to, last time we had just one of them, so we don't have to worry about this. But here we do have to worry about both a coefficient and two guys add up inside those brackets. And the first one should have been 121.2, is that right?
Yes, ma'am.
121.2 joules per mole Kelvin. And the second one is going to be 2 times hydrogen peroxide, which would be 109.6.
Yeah.
Did y'all get 109.6? If you didn't get any of these values, tell me now, because we'll see what mistake you made. My guess is going to be one of those mistakes that I just talked about. What'd you do? What'd you do?
I used water instead of hydrogen peroxide.
There you go. I didn't even. That's not one of them on there. I'm glad you said that. That's reading the compound incorrectly. H2O. So a lot of these compounds look alike. You saw that the other day when you were looking some of these guys up. Okay? So that's a sixth mistake, where I'm just looking up the wrong compound. All right.
Make sure you subtract and not add.
Now, the math, right.
Rich,
Minus this whole thing added together, and then subtract that. What do I get what?
The O2, like if you put H2O2.
All right, it's not O2, it's H2O2. That's the compound. I look him up. Hydrogen peroxide, H2O2. All right, now, at this point, by the way, here's the nice part about the way I grade, if you don't remember this from last year. If you have all that set up, how many points could you lose now?
No. 2 points?
No.
1 point.
1 point. Okay, that's because I'm so generous. If you hook all those up together that way, you could only lose 1 point. Now, I didn't say if you had, for example, if you forgot the 4, if you looked the wrong number up, each of those would be worth 2 points apiece. But if you looked up the right coefficients, and if you looked up the right numbers in the right columns, and you set it up like this, then all you do now is your math mistake, it's only going to be 1 point off. Okay? Which, by the way, if you do it right, what do you get?
130.7.
130.7 or something like that?
0.7, yeah.
Joules. Now, it's going to be joules per mole Kelvin, but in reality, what has canceled out of this? Because everywhere you multiply by one of these, you're multiplying, and this is a 1 there, you're multiplying by mole. So technically it's in joules per Kelvin, right? But I don't care if you leave it as joules per mole Kelvin. That's all right. All right, that is your answer. Let me ask you this.
So nobody was right.
I don't know. Did anybody have 130? Olivia, the only right person here. How about that? All right, listen. What does that tell me about this guy? Is he favoring spontaneity or not?
No.
It's a positive delta S,
No.
a positive entropy.
No.
Do things seek to be more disordered?
Yeah.
Yes.
What?
This
Why?
favors spontaneity. I just spent the whole first half of the class explaining why.
Wait, is it the delta H is the one that's supposed to be negative?
Yes.
Oh,
That's my
that's
point.
another one. You can mess that
I
up.
know. I spent that whole first half of the class showing you how when I drop the pen,
It goes
lower
up.
energy, negative delta H. But Allie's hair naturally becomes messy. Okay?
I feel like I got it.
All right.